Continuing on in Chapter 3, we move from measures of center to measures of variation. The first measure of variation that we're going to talk about is the range. The range is simply the difference between the maximum data value and the minimum data value. In other words, to calculate the range, we take the maximum data value and subtract from it the minimum data value. For example, let's look at this data set containing the numbers 9, 7, 10, and 13. To calculate the range, we'll take the largest data value, the 13, and subtract from it the smallest data value, 7. That means that the range in this case is 6. When we are calculating measures of variation and there's rounding involved, we want to carry one more decimal place than what's present in the original data set. This is the same round-off rule that we had for measures of center. Our next measure of variation is the standard deviation. The standard deviation is the average deviation of the data values from the mean of the data set. In other words, we want to know, on average, how far do each of the data values vary or deviate from the mean. When we are referring to the sample standard deviation, we will use a lowercase s. When we are referring to the population standard deviation, we use the Greek letter sigma. Notice that in each of these equations, you have the corresponding notation for the mean, x bar or mu, and for the size of the data set, lower or uppercase n. To help us understand the standard deviation, let's look at this data set containing the four values 5, 3, 8, and 4. So let's start by calculating the mean for this data set. We'll go ahead and talk about this in terms of a sample and use notation for a sample since we don't know where these data values come from. The mean, x bar, is equal to the sum of the data values divided by the number of data values. So we have 20 divided by 4, or a mean of 5. And I'm going to create a table of values to help us keep track of each step along the way, beginning with a list of our data values. In the equation for calculating the sample standard deviation, the first thing we need to do is find the difference of each data value and the mean. So we'll find x minus x bar for each data value. What we need to be able to add up is these differences squared. So in the next column, we'll take each of these differences and square them. Our first difference is 0, and 0 squared is 0. Our second difference is -2, and -2 squared is +4. Our third difference is 3, and 3 squared is 9. And our last difference is -1, and -1 squared is +1. Now we can add up all these differences. Adding up this column gives us the sum of each x minus the mean squared. And adding 0, 4, 9, and 1, we have 14. Now we have the numerator inside the square root for our standard deviation equation, and we're ready to calculate it. The standard deviation is equal to the square root of the sum of our differences squared, 14, divided by the number of data values, 4 minus 1. So we have the square root of 14 over 3. Putting that into our calculators to give us a decimal approximation, we find that the standard deviation is approximately equal to 2.2. Notice that I rounded to one decimal place because the original data values were given with no decimal places. One last thing to point out about these two equations for the standard deviation. You may have noticed that the denominator for sample standard deviation has an n-1 instead of simply an n. This makes allowance for the fact that sample standard deviations tend to underestimate the value of the population standard deviation, so we make this little extra adjustment. Variance is another measure of variation, and it's equal to the square of the standard deviation. For sample standard deviation, we use an s, so for sample variance, we use s squared. For population standard deviation, we had lowercase sigma. So for population variance, we have lowercase sigma squared. Notice that these two equations are equivalent to the equations that we just had for standard deviation, but without the square root, because we have squared both sides. Let's find the variation for the same data set that we just calculated the standard deviation for. we found that the standard deviation was equal to the square root of 14 over 3, or about 2.2. So the variance, s squared, is equal to 14 over 3 without the square root. And this is approximately equal to 4.7. Again, we're rounding to one decimal place because the original data set was given with no decimal places. Calculating the standard deviation by hand can be cumbersome. So if we only need a rough estimate for the standard deviation, we can use this range rule of thumb for estimating standard deviation. This rule tells us that if we want to just roughly estimate the standard deviation, we can take the range and divide it by 4. Let's take a look at our same example data set and compare this approximation to the standard deviation that we already calculated. The range for this data set is equal to the maximum data value, 8, minus the minimum data value, 3. So the range is 5. So to approximate the standard deviation, we'll take our range, 5, and divide it by 4. 5 divided by 4 is 1.25, and rounding to one decimal place, we have 1.3. Notice that that's pretty different from the actual standard deviation of 2.2. But depending on the circumstances, this might work in a pinch. Not to be confused with the range rule of thumb for estimating standard deviation, we have the range rule of thumb. The range rule of thumb divides a set of data into usual and unusual. Imagine that the mean of a data set is located here on the number line. We would expect some values to be less than the mean and others to be greater than the mean. After all, the mean is one of our measures of center. The range rule of thumb tells us that if we go 2 standard deviations below the mean, that serves as a borderline of usual and unusual. Let's add that to our picture. If we take the mean and subtract 1 standard deviation, we are now 1 standard deviation below the mean. If we take the mean and we subtract 2 standard deviations, we are now 2 standard deviations below the mean. And we consider this to be our dividing line between what is usual and unusual. More specifically, data values that are more than 2 standard deviations below the mean, we consider to be unusually low. We can say something similar moving above the mean. If we add the standard deviation to the mean, we are now 1 standard deviation above the mean. If we add 2 copies of the standard deviation to the mean, we are now 2 standard deviations above the mean. And that again is our line between what is usual and unusual. Data values that are more than 2 standard deviations above the mean are considered unusually high. All data values that are within 2 standard deviations of the mean are what we consider usual. Anything below is unusually low, and anything above is unusually high. Let's try out this concept with an example. The mean score of a test is 75%, and the standard deviation is 10%. We're going to use the range rule of thumb to determine the minimum and maximum usual scores. And after we've done that, we can determine if a score of 56% is unusual. First, let's write these percentages in terms of decimals or proportions. We have a mean of 75% or 0.75, and we have a standard deviation of 10%, which is 0.10. Usual values are no more than 2 standard deviations from the mean. So if we take the mean and we add 2 copies of the standard deviation to it, we have 0.75 plus 2 times 0.10. This is 0.75 plus 0.20, or 0.95. So that's our maximum usual value. That's the highest test score that would be considered usual. If we take the mean and subtract 2 copies of the standard deviation from it, we have 0.75 minus 2 times 0.10, or 0.75 minus 0.20, or 0.55. That tells us that a score of 55% is the lowest score that's considered usual. Let's draw a picture to go along with this. Let's imagine this number line goes from 0 to 100%, which is 1.00. Our mean test score was 75%, which I can locate here. 1 standard deviation below the mean is at 0.65, and 2 standard deviations below the mean is at 0.55. Similarly, 2 standard deviations above the mean is at 0.95. That means that all test scores that land between 55 and 95% are considered usual, and test scores below 55% and above 95% would be considered unusually low or unusually high. So, is 56% an unusual test score? No. 56% or 0.56 is just barely within the range of usual, so it's still considered usual and not unusually low. This brings us to what's called the empirical rule, or the 68, 95, 99.7 rule. For data that is normally distributed, about 68% of all of the data values fall within 1 standard deviation of the mean. About 95% of all data values are within 2 standard deviations of the mean. And about 99.7% of all of the data values are within 3 standard deviations of the mean. It's important to note that we do require that data be normally distributed in order to apply this rule. We cannot make these assumptions for data that is not normally distributed. Remember that normally distributed data takes on the shape of a bell curve, centered on the mean. We can mark this bell curve 1 standard deviation above and below the mean, 2 standard deviations above and below the mean, and 3 standard deviations above and 3 standard deviations below the mean. The empirical rule tells us that if we go 1 standard deviation above and below the mean, this captures 68% of the data values, which is more than half of the data. If we go 2 standard deviations above and below the mean, we have accounted for 95% of the data. And if we take it 1 step further and go 3 standard deviations above and below the mean, included 99.7% of the data, almost all of it. The range rule of thumb told us that data values that were more than 2 standard deviations away from the mean were considered unusually high or unusually low. Do you see now that those unusual data values only account for 5% of the data? With 95% of the data falling within 2 standard deviations of the mean, we have the final 5% divided into these 2 tails, with 2.5% in the left tail and 2.5% in the right tail. So our standard for unusually high and unusually low is accounting for only the top and bottom 2.5% of the data. To help us understand the empirical rule, let's take a look at this example dealing with body temperatures. Body temperatures are actually a bell-shaped distribution or a normal distribution with a mean of 98.2 degrees Fahrenheit, not 98.6 like most people think. And the standard deviation is 0.62 degrees Fahrenheit. We'll use the empirical rule and we'll approximate the percentage of adults who have body temperatures that are between 96.34 degrees and 100.06 degrees Fahrenheit. We can assume that these numbers came from a sample because they clearly didn't measure the temperature of every adult in the entire world. So we'll use our notation for sample data. We have a sample mean, X bar, of 98.2 degrees Fahrenheit, and we have a sample standard deviation, S, of 0.62 degrees Fahrenheit. We want to know the approximate percentage of adults that are between 96.34 degrees and 100.06 degrees. In order to use the empirical rule, we need to know how many standard deviations above and below the mean these 2 values are. If we first take our mean and subtract 1 standard deviation from it, we have 98.2 minus 0.62, or 97.58. If we take the mean and subtract 2 standard deviations from it, we have 98.2 minus 2 times 0.62, which is 96.96. We need to keep going. If we subtract 3 standard deviations from the mean, we have 98.2 minus 3 times 0.62, or 96.34. So 96.34 is 3 standard deviations below the mean. Let's check and see if 100.06 degrees is 3 standard deviations above the mean. If we take the mean and we add 3 standard deviations to it, we have 98.2 plus 3 times 0.62, which is exactly 100.06. Since 96.34 degrees Fahrenheit and 100.06 degrees Fahrenheit are 3 standard deviations below and 3 standard deviations above the mean, we can use the empirical rule to state that 99.7% of adults have a body temperature between 96.34 degrees and 100.06 degrees Fahrenheit. We will end this lesson by talking about Chebyshev's theorem. Chebyshev's theorem is similar to the empirical rule, but it doesn't require that the data be normally distributed. And while it does apply to all data sets, regardless of their distribution, it is only an approximation and does not give us the same accuracy as the empirical rule. Chebyshev's theorem states that the proportion of any set of data lying within k standard deviations of the mean is always at least 1 minus 1 over k squared, where k is any positive number greater than 1. For example, if we let k equal 2, we're asking the question, what proportion of the data is within 2 standard deviations of the mean? Chebyshev's theorem would tell us that at least 1 minus 1 over 2 squared of the data is within 2 standard deviations of the mean. That's 1 minus 1/4, or 3/4, or 0.75. So we know that at least 75% of all data values lie within 2 standard deviations of the mean. If k is equal to 3, then we're asking how much of the data is within 3 standard deviations of the mean. And we can calculate 1 minus 1 over 3 squared, or 0.89. That is, Chebyshev's theorem tells us that at least 89% of the data is within 3 standard deviations of the mean. To finish this with an example, let's suppose that we have a class with a mean of 75% and a standard deviation of 10% on their last test. We're going to find out what percentage was within 4 standard deviations of the mean. Since we're not told that the test scores were normally distributed, we can use Chebyshev's theorem to give us an approximation. Notice that Chebyshev's theorem does not rely on the mean or the standard deviation. We simply want to substitute k equals 4. We'll calculate 1 minus 1 over 4 squared, or 1 minus 1 over 16, which is 15 over 16, or 0.94. That tells us that at least 94% of the test scores will be within 4 standard deviations of the mean. That concludes this lecture video on various measures of variation.